Hi, hello, good afternoon, good morning, depending on your area. Thank you for attending to this webinar. This webinar is about advanced dynamic analysis using finite element method and using the software CivilFEM 2016. Roman Martin and along with me, Ronald Siet, will be the ones presenting you this webinar. Thank you for attending.
Hi, this webinar, as Ronald said, is about dynamic analysis in CivilFEM, the options CivilFEM has for this sort of problems. And this webinar will be complemented by the next one that is about seismic analysis. And it will be the 11th of October. And both of them will analyze all dynamic possibilities with CivilFEM, any sort of dynamic analysis, and especially seismic analysis. As an introduction, as you know, many problems are many structures that civil engineers, structural engineers has to deal with are dynamic problems, and using the static assumptions for equivalent static loads. We don't have many details about the solution solving with equivalent static loads. So dynamic is necessary in these problems. With CivilFEM, we will see all the possibilities we have doing in frequency domain, modal analysis and harmonic analysis, and also solving transient analysis. In transient analysis, we can add all sorts of nonlinearities, contact, material nonlinearities, large displacements. So with these nonlinearities, we can have a much more detailed analysis. To see all these options, we are going to solve these two models. The first one will be an offshore wind turbine with a monopile foundation, and the second example will be a mobile load on a curved deck bridge. CivilFEM has some options to model these mobile loads in a very easy and simply way. Just one of the most basic examples about and general examples nowadays about dynamic analysis in structural designs are offshore wind turbines. They involve all the actions that this sort of structure has are dynamic. We have wind loads. Here you can see wind loads in the wind turbine. Also, this sort of models will have the waves that are also dynamic. And it's very important also to model the soil. Frequencies depends about the soil around this monopile. So we are going to solve a modal analysis in this model to check the frequencies, a harmonic analysis, force it with some forces just to obtain the maximum response, and also a transient analysis with the same sort of loads to analyze in detail the response of the structure. And finally, we will perform an impact of a ship on this pile. For the modal analysis, it's very important to obtain the desired frequencies in a range of frequencies of the natural modes of the structure that avoid the resonance frequencies of the three sort of actions we have: the winds, the waves, and also the blades, the rotor blade. And here we can see in this graph. Here is the frequencies of one of the blades, the rotor. Here are the frequencies of the three blades that are 3 times bigger, 3 blades. And also here we have the wave spectrum, and wind loads will be the frequencies for wind loads are smaller around here. So the desired frequency for our structure should be around here. we need to find to design our structures just to avoid these zones, and just our frequencies should be here around. In the case we have a soft soil. So in this model we are solving, it's a soft clay. If we have more stiffener soil, we have to try to find the frequencies here around. So if we open the first example.
Yes, first of all, we open the CivilFEM. As you know, once you open the CivilFEM, you have many options. Once you open the launcher, you have by default a 3D static structural analysis, but you can always select a new one. In this case, we will choose a modal structural analysis. In case you have already done a structural analysis, you can always import your model and start from your geometry and mesh and loads, and then start with a modal analysis or transient analysis or whatever. So
yes, you can modify the analysis type and then import the model. So in one model you can solve all this type of analysis. Yes. So well, here we have the structure. The first part, this dark brown part, is the pile that is driven into the soil. Then we have the transition part that is just underwater, most of that, and over that we have the tower. Here on top it is the wind turbine, and well, we have modeled it with masses, 12 masses here around. So well, if we plot all the model, we will plot also all the soil. Here we can see the structure. Well, boundary conditions are normal to all the faces outside, and also in the bottom part. And well, the way to perform a modal analysis is after importing the model or generating the model with the geometry, etc., generating the mesh. Then here in solve, clicking here in the configuration, here we select the number of modes we are extracting. If we are extracting number of modes, we could also change it to frequency range. And we set here a frequency range, and CivilFEM will extract all the modes between that frequency range. Also, this modal analysis could be a pre-stress modal analysis. So we should solve a static model before, and then import the stresses for that pre-stress modal analysis. Well, after solving, pressing here, we extract all the modes, and here we can read those modes. Select the first one, and well, we can plot it. I'm going to plot maximum displacement, total displacement, just to be able to see the mode shapes. Well, also we have to click here to see the deformed shape. In these options, there's no deformed shape. Well, now we can see the mode. The first mode is just a bending of my wind turbine, and just without any movement here on bottom on the soil. If we advance to the second mode here, we can see it's similar but in the other direction. There are two symmetries here in the model, so it's the symmetric one. Next one. Well, the next one, it's also bending, but also there is a displacement of the soil, so it involves a soil mode shape. Also, if we click for information, we can see the modes, the frequencies, and well, all the rest of the information, all the masses and the directions of the modes. Well, we can see the first mode here, it's around 0.4. So if we check the slides, if we check the slides, well, we can see the 0.4 is, well, in the desired zone. If not, we can modify the model and just try to find the structure shape that just have the modes, the natural frequency modes, in the zone far away of the resonance frequencies. And here we have the list of the first 10 modes. The next analysis type is performing a harmonic analysis. We can perform a harmonic analysis with different sort of loads. We can perform a harmonic analysis with a force on top of the model. We are going to see it.
We have already solved our model, so we just need to open it. In this case, harmonic.
Just let's see the wind effect.
The model is the same as you see, the same geometry and the same mesh, same structural elements.
Well, okay, we plot all the model, and in this case, for the harmonic analysis, we have to define the harmonic load. It will be solved like a harmonic load as an nodal load. We can define with CivilFEM two different sort of loads. Just clicking here, load group, and we define different sort of loads. It could be pre-stressing loads, so it will be used for a pre-stressing modal analysis, and also the harmonic loads. In my case, I've defined the harmonic load like a punctual load here on top. That will be the effect of the blade rotors. Yes. Just clicking here, then I've selected that I'm having a harmonic load, then I select which sort of harmonic load, point load, and I apply it here on top. So, well, this is the load that I've defined it previously. I can plot it here. And well, you can see here on top, we have that punctual load. And then we perform the harmonic analysis. The next step here in solve, also configuration. And here in the configuration, we have to define the range for the frequencies. What I'm doing is starting from 0.01 hertz till 2, a big range bigger than the rotor frequencies. Pressing start, the software extracts the modes, and then we can get the solution. We have previously solved it. I'm going to results. I load the first result file. So, well, here also I can plot just graphs of any result against frequency time, in this case frequency. What I'm going to do is just plot displacement of top of this model. Here the node number, this node number is 40,459. So I can type it here. Also, I could click on the model and press OK.
It's interesting to see results versus frequencies.
Yes, well, here we can see the maximum response of that force for this range of frequencies. It corresponds to around 0.4. That is the first mode we had. Here we have other maximum value, local maximum, and here other that correspond to the other modes. The most important is this first one. Also, we can plot accelerations, X component of translational acceleration, also in the same node.
We can always plot until 10 nodes, so we can plot different charts in the same image. In this case, we're just interested in the one at the tip, at the top of the tower. And here you can see the other peaks of the X component translation of acceleration.
Well, these are the maximum response, but going to the previous graph of the slides,
here we have the slides.
Yes, here you can see these are the maximum response for displacement and accelerations, and these are the rotor frequency for one blade and 3 blades. So we can see that our design is valid because, well, the maximum response of my model is in this zone where there's no action. So I only have to take into account this part, these working frequencies, and also these working frequencies, and these are my maximum response for displacement and also accelerations. So, well, my design is valid at the moment with these two sort of analysis. Well, the next analysis type that we can do is a transit analysis. In the transit analysis with CivilFEM, we can include all type of non-linearities. In the previous model, we had contact between the pile and also the soil around. But for modal and harmonic analysis, contacts are taken into account as glue contact completely together. In this sort of analysis, we can have gap in that zone. Also, we can model nonlinear soil analysis and just have much more detailed results.
And nonlinearity as well for tower material. For steel, we can set a bilinear to take into account a possible yielding or collapse of the structure. Later we will see how to do it.
Okay. Well, my first example, the first example we are seeing is a transit analysis, but with free vibrations. So what we do is apply a horizontal load, keep it for 5 seconds, and then we remove the load. So it will have a free vibration. We are solving the same model, but, well, at the beginning we have to know, just when starting here, new, and just a selective transient analysis and importing the model. The steps are the same for all the examples. If we plot all the model, well, in this case, what we have done is apply a horizontal load. Now, as we are solving transit analysis, there's loads.
Depending on time?
Yes, depend on time. The way to define this sort of loads is defining a table. What we have done is applying a horizontal load. We can plot it here. Horizontal load. Here is the direction and the point of where it is applied, and with the table we have the value. Here, if we plot the chart, we can see that the value in kilonewtons is starting from 0 to 5 seconds. The load is increased until 1000 kilonewtons. Then we keep that load here for 5 seconds and remove the load. So there is no other load for 40 seconds. So it will have a free vibration. Also, just for having some more details, we have added to the model damping. The way to add damping in CivilFEM is the material. Here we select for clay. We have added a high damping value. We can define damping different ways. The way we use is adding the percent of the critical damping. In this case, we set 15% of the critical damping for soil. For steel, we added 5%. We also can define alpha and beta for the damping. Then we apply those loads and solve the model. Here you can see vibration. In the first one, we can plot results. Well, I remove loads. Example X displacement, plot. And here we can advance.
Depending how much time you put in the load case the time duration of our analysis and the time step.
Well, you can see here, there is just we've applied the load, and it will have the free vibration displacement. And well, we can also plot in the same way we did before, displacement of the top versus time in this case. So the way to do it is exactly the same here in plot, time frequency plot, and in the same node. And we click here, so we can get node results.
It's always interesting to plot results versus time, so you can see how is the behavior of that particular node or element along time.
Well, here we have the result. Here you can see we applied the constant increment of the load, but we can see even if we are applying a constant increment, there's just vibrations start. Also, we keep a constant force in this, but there is a small vibration, and then in this point in 10 seconds we leave it. So this is the response. As we define it, damping, the global damping of the model is just this reduction of the amplitude. If we don't apply any sort of damping to the model, this will be a constant amplitude of the wave. And well, if we see the slides,
so we go again to our slide. Here we go.
Well, here we can see this is the force we applied, this is the response, and also we can extract a video. We extracted a video with the results. We click here, keep the force, and then leave it, and the free vibration. Well, this is an example of how detailed we can analyze the model with this transient analysis with a nonlinear behavior of the soil, adding also damping and any other details contacts. Also, if this force is not well, just applied and leave it, like free vibrations, if we applied a cyclic load, also with the nonlinear soil behavior, what we can have is just nonlinear response between the applied force and the displacement of the model. With this sort of analysis, these cycling loads, we can analyze fatigue. In this case, CivilFEM does not check for fatigue at the moment, but you can get the maximum and minimum stresses in some of these cycles and perform just validate apart the fatigue of the model. And in this case, this is what we have done. Check the material degradation using CAM clay in the model. So well, if we click here, this is the response of the horizontal force of the displacement versus horizontal force in the model. This is the video we got, and we can see the displacement of the structure follows just like mainly a parabola.
Yeah, we'll see that there's a moment when the chart does not go always through zero. So there's always a displacement that is getting bigger. There's always a remnant.
Well, for this model to be able to perform a nonlinear analysis, taking into account the nonlinear behavior of soil, the way to do that is in the material, modifying the behavior, clicking here. We have by default linear elastic, but we can select Jacker bracket, more Coulomb, and special for this sort of analysis that with this cycling analysis where material properties are reduced, we can use the CAM clay model. For next versions, we will have also for tracker bracket and more Coulomb the cohesion and friction angle that will depend on plastic strain and will have hardening and or reduction of those properties. Well, clicking here can play, we can set the properties and solve the model as we did. Well, another important part for this dynamic analysis is the gravitational loads. The gravitational load masses shall be taken into account. With CivilFEM, it's very easy to model these added masses to the model. The way to do that is convert forces into masses. First, we define any sort of loads with any sort of shape. Here in the pile could be the hydrodynamic masses of water, but we will see another example that it's much more easy to understand, that is with the hydrodynamic masses of a dam.
Okay. Yes, to do this, we have just a short, easy dam to the dam, and we wanted to apply these hydrodynamic loads. These hydrodynamic loads usually follow not a linear shape. Usually they follow a parabolic shape following an equation depending on many parameters as for example height or densities or whatever. In this case, to define loads, you can use the typical utilities in CivilFEM, setting the loads, selecting our structural element, and then set their different loads, and we depend on any parameter. But it will be easier if we use some instead of the interaction, using the interaction mode, we can, or a graphical user interface, we can use another way of interacting, which is using Python as language, programming language.
Well, what we are doing is apply here the Westergaard equation, while the pressure, the hydrodynamic masses of the water of the dam that's moved together with the dam, just follow this equation. So what we have done with this macro, here on the bottom, this is to create the model, and the Westergaard loads are this part. And what we do is just applying on the nodes of the surface. Just here you can see, well, the node is selected in this loop, and here we calculate the pressure taking into account the coordinates that we get here in this two previously command. With the coordinates, we apply this pressure that is with this command applied to the model. It's very easy to apply. We can copy this, and here to load in the model, the steps should be just here, script editor, pasting it here. Well, we can just a new one, and just clicking play. So with these options, it will be applied on the model. We have previously done it, yes. So you can see here.
Yes, once we launch this formula, this Python commands, we can see how all the loads are applied for each node depending on its y coordinate. Depending on its height, it has defined more than 100 point loads, and we can see them here in the load group. Here we can see it's following a parabola. We can change we can scale the loads, the vectors, so we can see it better. You can see, or maybe can multiply by 3. Here you can see the shape of these loads.
It's parabolic, and well, just when we define our loads, any shape, just what we have to do is click here to convert them into masses. So very important. So CivilFEM will automatically convert this pressure into masses so we can perform the modal analysis or, well, any sort of dynamic analysis, transient analysis. And well, after seeing these three sort of analysis, transient, modal, harmonic, and transient analysis, the next solution that we did is a seed impact on the model. So well, for this model, we added to the previous geometry, we added a new structural element that is the ship.
Here you can see the model is the same. We have the soil, the pile, and the tower and the transition. But we added this new geometry to simulate a ship which will impact the transition geometry. What we want to do?
Well, first here we have to add to the model the initial condition. For the initial condition, here you can see, or here you can see in the initial condition, what we have added is a speed of the ship. The way to do that is here, add the new.
Always adding a initial condition, which can be velocity, and we select which structural elements will be affected to this initial condition. In this case, we use it because well, we want the ship is not far to the element to be in contact, because we wanted to solve as less results as we want, because we don't want to take many resources, because if it's very far, we will need to put a long duration of our analysis, and will take more resolve files and whatever. So we just set, well, a very close distance between them, and we just solve the analysis. We have to set always a contact between these two elements, which is very easy to set. Well, to contact elements, we just set here which will be the elements in contact. In this case, we have these two, and then we just need to set it will be glue or touching, breaking, advanced. We have many type of contacts. In this case, will be enough to be to set touching contact.
Well, the boundary conditions for in this case are the same as is previously models. For the soil, the normal constraints for the faces of the soil, and here you can see normal constraints of the faces of the soil. We can plot it on the mesh, and and for the boat, for the ship, the only boundary condition, initial condition is the velocity in x direction, and then we solve the model. Of course, after the crash, this could become a solid rigid motion and stop converging, but we solve just for 0.5 seconds after the impact happens. Here, in the load case, we define the calculation time. We have solved the model for 2 seconds. As we have the speed of 5 meters per second, we are sure it will crash before the end of the solution. Also, after defining the calculation time, before solving solution level, we define the initial the number of steps we would like to do. For this sort of analysis, we have to define a very small time increment.
Yeah, we can, if we want, in this case, well, if we want a portion of a second, we can divide each second or into 1,000 or in 100 or whatever. So after that, in this case, we have defined 200 load steps. So we have here the ones beginning in impact. So if we open the first one or any of it, and then we use our our navigation buttons. Here we can see our first solved increment, but we can go further, and we see here in the legend how the ship will move against the tower.
At the moment it didn't touch, but it will start touching in.
And if we go to the last one, we can see, and if we plot the formed shape, we can see how it is moving the pile.
Well, if we extract in the same way we did in the previous models, if we extract all the plots and the videos, we can see the video of the impact.
Yes, in this case we can always set all the results, and then see all of them in a video. And here we can see the displacement of horizontal displacement of both pile or the turbine and the ship.
And we can see also there's a rebound on top of the after the impact.
We added as well the non-linearity of the material. In this case, it wasn't enough this time. We can solve it with more time, so we can see the possible yielding and the final collapse of our structure due to plasticity. Just by setting the nonlinear behavior of our. If we open the same one, we can just go here, and here in analysis we can set it to be linear. So in this case we'll take into account the plasticity in our model,
and we can analyze yielding after the crack and well in detail of the damage of the structure. And well, after this seeing this model about all the possibilities of analysis we have for dynamic analysis, that is modal, harmonic, transient analysis with all sorts of non-linearities, and the tools we have, that is adding damping to the model. Of course, also all sorts of non-linearities can be solved for transient analysis. Also the option of converting gravity masses into gravity loads into masses, and to take into account hydrodynamic masses or any other sort of masses. The last tool we have is a mobile load on any sort of surfaces. In this case we have solved other type of structure that where dynamic effects are very important. That is a steel bridge. They are with the long span bridges, steel bridges, the dynamic effects are very important. So what we have done is solve also dynamic loads, that is over the deck. We are going to open the example.
As we launch CivilFEM again.
In this case, it is also a transient analysis. Okay. Here you can see the model. Just taking it from bottom, we have I-beams. Here we have some stiffeners here on the bottom, and also for the torsional effect on the left side of the model, we have added some extra green color stiffeners for improving the lateral buckling effect of these girders. And well, what we are going to do is also solve the model with a traffic loads over this deck. It's very easy to define loads. these mobile loads here. So the way here, we click in loads, load group, new loads, mobile load, click here, OK. And then the place where to define it is clicking here, point modal load. So now we have to set here all this information. The name of this mobile load is the name we would like to do, heavy vehicle, an example. And then we have to select the structural element where this load will be applied. In my case, it's here in the deck. So clicking here, I defined it. And also, very important, the path. Inside it, we select the curve where these loads will follow. After selecting it, we set the force and the direction, could be horizontal or vertical, and a percent of horizontal load, that could be a percent of vertical load, the initial time for this load, the speed, and the number of steps I would like to divide. I know the length of the bridge, so I set here the speed and the initial time, and the model will solve all the loads. I've done this previously, so here we have my loads, and I can plot them, clicking here, loads, load case, this one. So here I'm plotting boundary condition and the loads. Well, here you're seeing all loads together, but of course they are applied in 4 points, and then they advance for all these directions. Well, the distance between the first four loads and the next ones depends on the number of steps we have defined. As we see previously, we can define here, when I apply here, we can define the steps. So the length is divided between the steps. If we would like to apply much more, we divided it. Well, and after this, next step is solving, and we can configure also the solutions here with the initial and final time, adding here the fractions, the time increment, also damping, and any other value could be add to the model, and then we solve it. After solving it, we read results. Here we have solved it.
So we will have one result file for each position. As you know, these forces will generate each position, but as the vehicle will occupy only one position at a time. So it will solve as many positions or load the configuration that we have.
I've selected just one load step in the middle, so these are the displacement, but well, we also can plot any sort of result, forces and moments, wherever, and check the model for any type of checking type the steel structure, such as well all these. We can check by code all these stiffeners and all the beams. Well, we can check the effects of these mobile loads in these slides. We also have extracted 2 videos. In the first one here on top, we are plotting a vertical displacement. So the mobile load, we can see it's advancing in that direction. And here we are plotting for MISEC equivalent stresses. And well, for stresses, it's much easier to see where the loads are applied, these loads of the traffic vehicle over my bridge. So well, as a summary, we had an overview of some of the tools CivilFEM has for dynamic analysis. We will have, as I said before, on 11th October, the next webinar that is about seismic design, seismic analysis. So we will complete with that webinar all CivilFEM tools about dynamic analysis. So those are modal, pre-stress modal analysis, harmonic, and transient with all sort of nonlinearities that can be solved this sort of models. Also, we saw an impact, and we can see with CivilFEM, it's pretty easy to work with nonlinearities and well, so to solve all type of analysis. Well, for our just checking next webinars and next information, you can go to the website CivilFEM.com, and well, here we have the website.
Yes, always visit our website, and of course, not only our website, you can follow us always using Facebook, Twitter, Google+, YouTube, and our LinkedIn. And as Roman told you, we go always to resources.
Yes, here in resources, you can check here in webinars and check when are the next webinars. The next one will be the 11th of October about the seismic analysis. And also you can check here in this from the partners for the nearest local partner in the countries where you are, if you need some other information, or also if you would like to check CivilFEM, and if you would like a demo version for checking the software.
Yes, and always, well, you have here our contact emails and names for any information you need or regarding our software, commercial, sales, or management, anything.
Well, thank you very much for your attention.